Welcome back for another AP Pre-Calc video. Today we're talking about kind of 1.9, 1.10. We're still talking about rational functions, and we're really going to start discussing holes in vertical asymptotes in a little bit more detail in regard to limits. So this is more of a calculus-heavy lesson with the idea of limits. This is definitely something that will prepare us for calculus next year. So let's go ahead. Let's look at a few examples of just finding holes in vertical asymptotes. So first, remember, holes are where you have canceled terms, right? Holes are the canceled parts. And vertical asymptotes is after you cancel stuff, anything left on the bottom, set the bottom equal to 0. Well, notice for f of x, you could cancel the x plus 3's, and all you're left with then is x minus 2 over x minus 5. So, okay, what I'm left with then, or what the holes in asymptotes are, is I would have a hole at the canceled part of x plus 3 equals 0, so there's a hole where the x value is negative 3. Your vertical asymptote is the bottom. The bottom is at x minus 5. If I were to add the 5 over, there'd be a vertical asymptote at x equals 5. Right? So pretty basic idea. This can get a little bit more complicated when we look at something like this next expression, this next function. And let's see how this one simplifies. One thing we can do is I have x minus 2 squared on top divided by x minus 2. If I were to just look at the x minus 2's, I would have something like this. X minus 2 squared on top, that's x minus 2 times x minus 2. And on bottom there is still that singular x minus 2. So if I were to cancel those, the one on bottom goes completely away. The one on top no longer has the squared part. I can get rid of 1 from the top and the bottom. Same idea with the x plus 1's. There's 1 on top that would go all the way away. You have 2 of them on bottom, so you get rid of 1 by slashing out the exponent. All I would have left is x minus 2 over x plus 1. Okay, that's the idea of using exponent rules there. So if I look at the hole, then we would have two different holes. One of them at x plus 1 equals 0, so x equals negative 1. And the other one, if I set x minus 2 equal to 0, I'd get x equals 2. We have found two different holes on this graph. The vertical asymptote then would be your simplified form, taking whatever's on the bottom and setting that equal to 0, and notice I get x equals negative 1 again. Well, now you're saying there is a hole and a vertical asymptote at x equals negative 1. That's not really allowed. You can't have a hole at the same spot as a vertical asymptote. So really what you end up finding is that the vertical asymptote takes priority. You're going to have an asymptote at negative 1, and then the hole, we kind of disregard that at this point. Okay, we can still state by finding both of them, but once they're the same, the vertical asymptote definitely takes priority. Let's look at h of x. This one, what you would notice is the bottom is not in factored form, so you could actually factor the bottom before we do anything to give us 1 over. You could take an x out of both terms. I know some people in class wanted to separate this to be x minus 2 and x plus 2 because they saw x squared and 4. But realize that would be using difference of squares formula. This is a sum of squares, which is actually not factorable. This is a common misconception. The bottom is already factored as much as possible once you take that x out. X squared plus 4 is not factorable. If it was a minus instead, it would be factorable. Hole, it doesn't look like anything cancels when I look at this problem, but vertical asymptote, you need to take all of your different parts that are multiplying, right? Usually it's different parentheses, and we set each of those equal to 0. In this case, though, I just need to separate it again and set each part equal to 0. It's just weird in this case because there is an x, and people get confused by that for some reason. Okay, but the x does get set equal to 0 as well. If you were to solve this second equation, you would end up getting x equals plus or minus the square root of negative 4. If you take the square root of negative 4, that gives you I. So remember, the square root on both sides gives you a plus or minus. The square root of the negative gives us I. These are imaginary asymptotes, right? Because of the I there. If you were to graph this on the normal coordinate plane that we see, you're not going to see either of these, the positive 2i or the negative 2i, as actual vertical asymptotes on the graph that we're used to. If you were to graph this on an imaginary plane, that might be different. But on a normal Cartesian plane, those will not show up. Okay, so finding vertical asymptotes in holes, we know that idea. The main discussion was really around the second problem, where we can start to simplify these different parts if they do have these weird exponents. Okay. When you start to look at asymptotes and when you look at holes, one thing you can do is start to write limit statements. We've talked about limits going towards infinity. We've said we've done a lot with end behavior, where if your limit of x goes to positive or negative infinity, you're looking at the left and the right side of your graph with no bound, right? It just goes forever and ever. Where does your graph go? Is it stuck next to a horizontal asymptote? Does it go up forever? Does it go down forever? Those sorts of ideas. But what we want to do right now is we want to talk about limit statements based off of holes and vertical asymptotes. The reason you can do that is you get 3 different cases that could happen. If you have a hole in your graph, right? Let's just draw some sort of rational function. Is it going to draw? Okay, let's just draw some sort of rational function. Maybe it looks like this. You got asymptote, asymptote, just a quick drawing. And let's say there's a hole right here, okay? Well, if you have a hole, your graph cannot equal that exact spot, right? It gets close to it, and because there's a hole, you'd have to technically jump over that exact value. So because you can't actually have that value, you can talk about either side of it. On the left side, as you get extremely close to the hole, what value are you getting close to? From the right side, as you get extremely close to the hole, what value are you getting close to? And realize, because you're just jumping over that spot, those two values should ideally be the same. If you were to have a different graph, let's say, let's talk about the vertical and horizontal asymptotes. If I were to have a vertical asymptote here, okay, I don't really care where my horizontal one is. Maybe it's down here. But what could happen is your graph could go in 2 directions, right? The ends, as you get close to these asymptotes, they end up going off towards infinity in the y direction. It goes up forever, it goes down forever, right? And both ends could go the same way. They both could go down or they both could go up, but they are going to go off to infinity. So we need to figure out which of those is happening. At vertical asymptotes, your limit will always go towards an infinity, and at a hole, your function will always go towards an actual value. Let's look at the differences here. What we're going to do is talk about left and right limit statements as x approaches 2. So there might be other holes or other vertical asymptotes, but I'm only curious about the ones occurring at around x equals 2. Notice on this first one, I get x minus 2 is a vertical asymptote. Well, vertical asymptotes, we said that that would be the second case down here where it's going to go off to either positive infinity or negative infinity on the left or the right side of that asymptote. So we're going to talk about our limit as x is going to 2. But we need to talk about both sides because you can't actually have 2. There's an asymptote there. So if I want to talk about the left side, you put a little negative up in the top spot there. We're looking at our function f of x, and I need to know what's happening. Well, how you can do this is you can use what's called a test point, where you can test the left side of 2. Well, you want to choose a value that's extremely close to 2. You can maybe say like 1.9 or 1.99, and that can be your test point. So if I were to use a test point on the left, let's say I'm using 1.9. That's to the left of 2. So that would mean I plug in 1.9 to each of these parentheses. And I don't really care what these values come out to. All I want to know is whether it's positive or negative. Because if it's positive or negative, that tells me which infinity it's going to. We already know it goes to infinity. I just need to know which. So if I look at my parentheses, the 1.9 minus 1, that would be positive. 1.9 plus 3, that would be positive. 1.9 minus 2, that would be negative. This entire fraction, then, there's only one negative. There's an odd amount of negatives. That means the entire thing would be negative. So the left side of our function, the left side of 2 for our function, goes to negative infinity. That's exactly what you want to do for the right side as well. But now I need to use a right test point. When I'm talking about the right, I want to create my limit statement. So we were talking about 2, but the right side of 2. So now I'm looking at positive for that. Well, okay, the right side of 2, let's plug in a test point. Maybe let's use a value of 2.1. It's close to 2. And I want to know, is that positive or is that negative? 2.1 minus 1 is still positive. 2.1 plus 3 is positive. And 2.1 minus 2 is positive. There's no negatives here, so the entire thing would be positive. That means the right side of this must go to positive infinity. That would look something like this right graph. The left side of 2 goes down to infinity. The right side of 2 goes up towards infinity. It would look similar to that graph. Let's look at another example. This time, we're going to be discussing a whole. Notice x minus 2 does cancel. So x equals 2 is a whole. Well, this last one, we needed to test whether our function was positive or negative to figure out which infinity it goes to. The reason we had to do that is because x equals 2 was a vertical asymptote. But since x equals 2 is a whole on this one, we know that we're going to get some sort of value. So I don't care whether I get a positive or negative. I care about the actual number now. So to do that, what you do is you plug in the actual value. Right? If I need to know the y value, I want to figure out what I get as an output. That means I need to input something. So I'm going to input 2 into our reduced fraction. 2 plus 4 over 2 minus 3. Figure out what that gives us. It looks like you'd get 6 over negative 1, which is negative 6. So we end up getting a whole is occurring at 2, negative 6. But I need to talk about the limit as we get close to that whole. Well, again, because I can't have negative 6 on this actual function, I need to talk about the left side of 2, and I need to talk about the right side of 2 for our function g of x. So since our function approaches a hole, what that would mean is somewhere on your function, right, it might look something like this. We're going to get to this coordinate 2, -6. So on the left side, your graph is still getting close to that y value of -6. The right side of your graph, it's still getting very, very close to that y value of -6. Both sides get super, super close to it. And then that exact hole value, you just jump over it. Both sides do approach that spot. Whenever there's a hole, you should get the same value. And again, for the hole, you can find that by plugging in. Let's look at one more example if you need to see this last one. It's just a slightly different. So if I were to simplify our function, right, the x minus 2 goes away, the squared goes away. So I have x minus 4 over x minus 2, x minus 1. So what you'd notice is, okay, there might be a hole at x equals 2. There might be a vertical asymptote at x equals 2. But remember, at the beginning of the video, we said that vertical asymptotes take priority. So there's going to be a vertical asymptote at 2. We're not going to get an actual value. It is going to go off towards one of the infinities. Okay? So, okay, let's think back to 2 problems ago. We said if there's a vertical asymptote, you have to use test points and figure out whether it's positive or negative infinity, right? And you can do that by just choosing a value close to the vertical asymptote. So I can choose a value close to 2. Again, I'm not worried about the other vertical asymptote, x equals 1. Specifically for these problems, we're just looking at x equals 2. If it did say discuss all the vertical asymptotes, yes, you would have to discuss both. But let's create our limit statements for the left side of 2, again with the little minus, and the right side of that as well with the little plus. So, okay, the left side, let's use our test point. Left of 2, that would mean less than 2. Let's say 1.9 again. And when I do this, okay, I'm going to go to the simplified form, plug in there, see what's actually happening. 1.9 minus 2, 1.9 minus 1. That's a little sloppy. Let me fix that. Okay, so we have something like this. Again, I just care about positive versus negative. Top would definitely be negative, it looks like. The bottom, 1.9 minus 2, that would be negative. 1.9 minus 1, that would be positive. Now, notice the amount of negatives, right? There's a negative over a negative. There's an even amount of negatives, so that would mean that the left side of this function goes up to positive infinity. Let's look at the right side of this function then. Well, the right side, so the right side of 2, I need to test that. Let's say 2.1, because that's bigger, that would be on the right side. Let's say 2.1. Well, 2.1 minus 4, 2.1 minus 2, and 2.1 minus 1. Let's see what that gives us. Top would still be negative. Bottom, 2.1 minus 2, that's going to be positive now, and 2.1 minus 1, that's still positive. Check to see how many negatives there are. There's only 1. That's an odd amount. This function then would be negative. So, okay, that means it goes to negative infinity around the vertical asymptote. So if you were to graph that, here, let's say is 2. There's a vertical asymptote there. The left side is now going up towards infinity. The right side is going down towards infinity. That is our 1.9, 1.10 video. Really, this is a heavy calculus topic looking at these different limits. But thanks for watching. That is another AP Pre-Calc video.